Well, hello folks. Welcome to Doc Onco Physics. Keith Onco here. What we want to look at today is sort of an introduction to light reflection in mirrors, otherwise known as geometric optics. So what we're going to be doing is just giving an overall general overview of geometric optics, and then in other videos we go into more detail, for example, Snell's law, diffraction, things like that. So today it's more of an overview, and then you can look to other videos for more specific things. So let's take a look at light reflection in mirrors. So very basically, all light is a form of electromagnetic energy. The light that we can see, the visible range from the red all the way to violet, right? These are the colors that we can see, but the electromagnetic spectrum is a much larger range of waves that exist. Some of them are harmful, some of them are not, but we've probably heard of most of them. In fact, the ones that we can see, right, would be right in there. That would be the visible range. But then we have some other ones that we know about, the ultraviolet range, right? When we go outside in the summer or when the sun is strong, we should wear some kind of UV protection. That's so we don't get our skin damaged. Then of course there's X-rays. Some X-rays are useful, but they're all fairly harmful. You don't want to go overboard getting X-rays, and X-rays are generally used to to see what's going on inside the body. And then of course there's gamma rays, and we don't ever really want to get hit by any of those. And those are given off in different types of nuclear reactions. Then on the other side we have infrared. Infrared rays are heat, like the heat that we feel from the sun comes from infrared. We have microwave, believe it or not, which is a very low energy wave, right, is on the other side of the spectrum. And then finally we have radio waves way down here, and the radio waves are an extremely low energy wave, but we use them for communication all the time. So these are the different types of light in the electromagnetic spectrum. We're going to mainly be looking at the visible light, the stuff that we use to be able to see. So a few facts about the speed of light, okay, or light. The speed of light is a constant in a vacuum, right? And that constant is approximately 3 × 10⁸ meters per second. Now, the speed of light can change, right? And it will change depending on the medium that it's traveling through. For example, if light is traveling through glass, it will travel at a slower speed. If light is traveling through normal air, our air is not very dense, and so we consider it to be almost like a vacuum. And so we still consider the speed of light to be 3 × 10⁸ meters per second. If light is traveling through water, it slows down. So depending on the medium that light is traveling through, it'll travel at a different speed. Now, some of the things that can happen to light when it hits an object is, one thing, it can be reflected, right? So you think of a mirror. A mirror reflects a lot of the light. It doesn't reflect all of it unless it's a perfect mirror, but most mirrors will reflect some percentage of the light, and that's what makes a mirror useful. The light can be absorbed, right? Like you think of a black piece of paper. When light hits a black piece of paper, most, if not all of that light is absorbed, okay? And none of it is reflected, which is why we see the paper or the object, whatever it is, to appear black to us. The other thing that can happen is, when light hits an object, is that it can be refracted. Refracted just means that it can bend. Okay, so the light hits some type of an object and it can bend, and the thing we're most familiar with would be glass or eyeglasses and lenses. When light hits a piece of glass at an angle, that light is going to bend in some way, some fashion, that can help us to see. It can help us to see whether we're nearsighted or farsighted, and those are some of the things we're going to talk about. So 3 things can happen. It can be reflected, it can be absorbed, or it can be refracted. Okay. Down here we have sort of a 3-dimensional view of what an electromagnetic wave looks like. It's an interesting wave because it's 3-dimensional. All right. It doesn't just have a 2-dimensional component, but on the X and Y axis we have the electric part of the wave, And on the z-axis, if you will, we have the magnetic part of the wave. And it's a self-sustaining wave. It can go on forever and ever and ever. All right, so it's an interesting type of wave. We're not really going to get too much into the characteristics of electromagnetic waves in this chapter. We're really going to talk about sort of at a higher level as just what happens to a ray of light when it strikes an object. So we're all familiar with mirrors, right? Over here we have sort of a diagram or a picture of a plane mirror that's in blue over there. And what happens when light hits a mirror is it is reflected, okay? Not all of it is reflected, but a certain percentage of it is reflected. That's what makes it a useful mirror, okay? There's a law of reflection, and the law of reflection states that the angle of incidence, which is this angle in here, let me change the colors here, this angle in here, right, we have an angle in here, that would be the angle of incidence, is going to equal the angle of reflection, okay? So this line here coming down in the center, and I'm going to sort of draw this in black here, okay? That line coming down in the center is a line that is perpendicular to the surface of the mirror, okay? And it's called a normal line. Normal in this sense just means perpendicular. So this normal line, all right, coming down here, perpendicular to the surface of the mirror, all right, is the line that we're going to measure the angles from, both the angle of incidence and the angle of reflection. We don't use this area in here or in here. It's the area here and the area here that we use for incidence and reflection. So you can see that the incoming ray, right, is where we have the angle of incidence, and the outgoing ray over here is where we have the angle of reflection. And again, the angle of incidence must equal the angle of reflection. So here's a question. Let's say that we have a plane mirror, right? And by a plane mirror, I mean a mirror that is flat. There's no curve to it at all. And we have an object over here, right? And if we were looking over here, say we had our eye over here, right? And we were looking towards the mirror, where would we actually see the reflection of the mirror, right? Would we see it behind the mirror over here? Or would it appear to be behind the mirror? Would it appear to be right at the mirror, right here? Or would it appear to be on the same side of the mirror as the object, right? So there's really three different possibilities. So one of the things that we want to talk about, or one of the terms we want to define, is something called the object distance, right? The object distance is the distance of the object from the mirror. So this would be DO right here, okay? And that's one of the terms that we're going to have to get used to. So that's the object distance, and it's always the distance from the object that we're interested in to the mirror, or when we get to lenses, the lens, or the piece of glass. So the question we had before was, where do we, if we're looking, right, at this mirror, right, and this candle is right there, where is it going to appear that the candle actually is? Well, if you guessed this, then you guessed right. It's going to look like the candle is actually somewhere behind the mirror, right? It's not going to appear as though the candle is in front of the mirror. It's going to appear as though the candle is actually behind the mirror, right? And when we have a system like this image here that we would see is known as a virtual image, all right? And it's virtual because if I was to put a piece of cardboard or paper behind the mirror here, where the image appears to be, there would be no image on the actual piece of paper. I wouldn't get anything. And that makes sense because all of the light, right, that is traveling from, say, this candle that's hitting the mirror, right, is being reflected, right? This ray would be reflected straight back, right? This one, say when it hits the mirror, it's going to be reflected off in that direction, right? Because remember the angle of incidence and the angle of reflection. They're all going to be reflected. So all of the light is going to be on this side of the mirror. There's not going to be any light on this side of the mirror. this would just be dark. Okay, so that's why this is known as a virtual image, because if I put a piece of paper back there, there would be no actual image of the object. Okay, so we've talked about an object distance. All right, we've defined that the object distance is the distance from the object to the mirror. Well, we can also have an image distance, right? And the image distance would be the distance from the image to the mirror. In this case, it's a virtual image, but that's okay. It still appears as though it has some distance, right? And in this case, DO would equal DI. The object distance would be the same as the image distance, all right? And their heights would be the same as well. And it's really only because the mirror that we're dealing with is a flat mirror or a plane mirror. When we get into curved mirrors, things get a little bit more interesting. Okay, so in this case, DO and DI would be the same thing. So let's say we have two situations here. We have this one here with just a box sitting on maybe the ground or maybe just suspended there. And we have a person over here. Let's look at what the person sees, because when we look in a flat plane mirror, we see an image of ourselves, right? Well, what's actually happening? Well, the object is over here, right? The object being your face and your hair and neck and everything else, right? Well, light that is coming from, say, this point to the top of the person's head hits the mirror here and then reflects off of the mirror into the person's eye. So from the perspective of the person who's seeing that ray of light, where does it appear that that ray of light is coming from? Well, they see it at this angle right in here. So from their perspective, it seems like that the ray of light is coming from some point back here behind the mirror. And the same thing goes for the chin of this person, right? There's light coming from the person's chin, hits the mirror, up towards the eye. Now, where does it appear as though the chin is for this person here? Well, it appears as though it's coming from this point over here, a point behind the mirror, which is why when we look into a mirror, the image that we get appears to be somewhere behind the mirror when we look in a plain flat mirror, right? And it really all has to do with the light that is being reflected off of our faces, right? Top of the head, chin, nose, whatever it might be, that's then being reflected back into our eyes, okay? And depending on what that angle is, right, our perception of that light is that it is coming from the angle in which it enters our light or hits our eye, right? So up here, it appears as though it's coming from over here. Down here for our chin, it appears as though it's coming from here, okay? And remember that the only reason we can see anything is because light is actually coming into our eyes, right? If we were in a completely dark room with no windows, the doors are shut and there's no lights on, we can see nothing. And the reason we can't see anything is because there's no light being reflected into our eyes from any object. And as soon as we turn a light on, right, whether it's an overhead light or a lamp or whatever it might be, that overhead light or lamp is shining onto all the objects in the room, and then that light is being reflected off of those objects into our eyes. That's how we can actually see. We must have light coming into our eyes to see, and depending on the angle of that light, that'll give us an idea as to where that object actually is, okay? So I talked about a virtual image, and there can be virtual images, right? But there can also be real images, all right? So we can have virtual, we can have real. So when do we get a real image? Well, for a mirror, when the image is on the same side of the mirror as the object, then it is a real image, okay? If we look at this picture here, we have a severely curved mirror here, and we have some kind of an object out here. Oh, make it green here. So we've got some kind of an object out here, and usually the objects are written as arrows because it's very easy to draw an arrow. So, and when we look at light from an object, typically what we'll do is we'll look at, there's an infinite number of rays of light coming from an object, but we can't deal with an infinite number of rays, so we only deal with one or two or three of the rays, and we can usually figure out what's going on if we just look at those few rays. So let's look at a ray of light coming from the top of the object here. And what's going to happen when it hits the mirror? Well, remember that for mirrors, right, we have the law of reflection, which is that the angle of incidence has to equal the angle of reflection. All right. So here we have a perpendicular line to the surface of the mirror, right? This line right here. And so we have an angle right in there. We have an angle right in there. And those angles are going to be the same. Okay. And so an angle, a ray of light coming in is going to hit the mirror. It's going to reflect, and it's going to go off in that direction over there. Okay. Now let's say we took another ray of light. Okay. And this ray of light would be this one. It's going to come from the top of the object as well, except that it's not going to come at this angle into the mirror, but it's going to come at another angle into the mirror where it goes through, say, the center point of the mirror, and the center point is basically the radius of curvature of the mirror right there, right? So this light travels through the center of curvature, hits the mirror right here, and then reflects back on itself, right? Because right here, it's coming in perpendicular to the surface of the mirror. Well, when we talk about rays of light that are perpendicular, right, to the surface, when that ray of light hits the surface, it's just going to come back on itself and go straight back where it came from. So in this case, what happens is we get an intersection between the two rays of light. And where that intersection is where our image is going to be. So we had an object over here, and we've got an image over here. Now, what do we note about that image? Well, the object itself was upright and large. In this case, the image, in this particular case, is smaller, right? And it is upside down. And depending on the location of the object, right, its distance from the mirror and its distance from something called a focal point, right, where it is in reference to the focal point, we're going to get different types of images, or we can get different types of images. They can be right side up, they can be upside down, they can be larger, they can be smaller, and it all depends on how the rays of light come from the top of the object, right, hit the mirror, and then are reflected off of it, right? And we're going to go through the rules of drawing these rays of light, all right, and we'll go through that in a little bit. And in fact, when we actually draw rays of light coming from, say, some object, I should have put this on the last slide, and they come and they hit a mirror and they reflect off of it, these are called ray diagrams. Okay, and what we typically do is we try to find 2 or 3 rays of light that reflect off of a mirror to find out where the image is. Now, we can have 2 types of mirrors. Well, we can have 3 types of mirrors. One's the flat or plane mirror, and that's somewhat interesting, but not all that interesting. Or we can have a mirror over here, and this is known as a convex mirror. In the old style stores, before we had all kinds of cameras all over the place, they used to put these in corners of stores. And why'd they do that? Well, they put them in corners of stores because the person looking into that mirror could see all over the store. It gave them a wide image of the store. Okay, they're not used so much anymore. Now we use cameras. The one that we're probably more familiar with is a concave mirror. And these are typically used in bathrooms. And why is that? Well, we can take a concave mirror and we can get our face really close to it, and we can see up close and personal all of the different things in our face. Our nose looks a lot bigger. All the pores of our face look a lot bigger. But a lot of people will use that for putting makeup on, things like that. So we'll use concave mirrors probably a lot more than we'll use convex mirrors. And as far as the name is concerned, the way to try and remember it is if the mirror is caving in towards you, right, then it's a concave mirror. Right? Convex is, and if it's not concave, it's convex. That's probably the easiest way to remember the names. Okay, well, a concave mirror is also known as a converging mirror, and that's the name that I usually use. And it's a converging mirror for one particular reason. In a converging mirror, the rays of light that are coming in are going to strike the mirror, and they are all going to obey the law of reflection. So at any point here, right, there is a perpendicular line, right, a very small, infinitesimally small perpendicular line that this ray of light here is going to hit, and it is going to be reflected off, right, using the law of reflection, right, angle of incidence and angle of reflection. So that this ray of light here, this ray of light there, the same for all of them. Now this ray of light in the center here is coming in perpendicular, so it's just going to bounce back on itself. But if you notice, all the rays of light that are coming in get reflected, and they get reflected to a point that is in front of the mirror. And this point is called the focal point. It is where all of the rays of light come to a focus, okay? And these rays of light here are coming in fairly parallel. We'll say that they're coming in from infinity, right? These are all parallel, these rays of light out on the left here. But once they hit the mirror, they get reflected and they come to a focal point. So the focal point is where all of the rays of light are going to come together. All right, they're going to focus at that point. Notice we also have another point out here called the center point, right? The center point is basically the radius of curvature for the lens itself. For the mirror itself, the mirror surface. So the center point is the radius of curvature for the inside surface of the mirror, right? And C will equal 2 times F. All right, so the distance of the length of the center point is going to equal 2 times the distance of the focal point, right, or the focal length. Okay, the distance between the mirror and the focal point is called the focal length. Okay, so we have focal point, we have focal length, and we have the center point. All useful things, and again, just more definitions as we get into geometric optics. All right, so a few more definitions. All right, again, we've already talked about these. C is equal to 2 times F, or F is C divided by 2. Over here we have a line that is perpendicular to the center of the mirror, and this line is called the principal axis. Okay, so we'll refer to that, and really that's a reference line for all of the rays of light. So we have this principal axis that's coming in straight, right, comes right into the center of our mirror or lens. Later on when we get to lenses, we have our focal point, we have our center of curvature, right? And those are most of the definitions that we're going to be using. So let's talk about ray diagrams. If you look out on my website, I have ray diagram cheat sheet, right? And what this does is it gives you rules for drawing light rays for both lenses and mirrors, okay? And there's essentially 3 rules for drawing the light rays, depending on whether it's a mirror or whether it's a lens. Okay, right now we're dealing with ray diagrams for mirrors. And the first rule is that you draw, I should do this in another color. You draw a ray of light coming from the top of the object, and it's going to be parallel to the principal axis, right? So the space between here and here, right, doesn't change. So it's going to be parallel to the principal axis. It's going to hit our mirror, and it's going to reflect off of our mirror through the focal point, and then go on down here towards infinity. Then you draw the line as long as you can, but you know the measurements and geometry of a paper may make it impossible to go on for infinity, but you draw it as long as you can. All right? So that's rule number 1. You draw a line that is parallel to the principal axis. It strikes the surface of the mirror, reflects off of the mirror, and goes through the focal point. So that's rule number 1. Now I guess one of the things I forgot to mention is, what's the point of drawing these ray diagrams? Well, the point of drawing them is that so we can figure out where the image is. All right, we can predict where the image is going to be. So the red line on here, the red ray, was the first one that we drew. Now we're going to draw a green ray of light, also coming from the top of the object. All right. Well, this ray of light is, instead of going parallel to our principal axis, this is going to go from the top of the object through the focal point on this side of the mirror. It's going to strike the mirror at this point right here, right? And it's still going to obey the law of reflection, right? So we have an angle of incidence, we have an angle of reflection, and this ray of light is going to travel back parallel to the principal axis. So this is ray number 1, this is ray number 2. So rule number 2 is we draw a line that starts at the top of the object, goes through the focal point, hits the mirror, right, and then reflects off of the mirror parallel to the principal axis. Okay, that's rule number 2. Now, we typically only need 2 rules to find where our image is. What we're looking for is we're looking for the point where the 2 lines, after they reflect off of the mirror, and it's important after they reflect off of the mirror, not before. So it's this line here, this ray here, and this ray here. Where do they intersect? Well, they intersect at a point right here. Okay, and this is where our image is going to be. Now note that the rays of light started from the top of our object. Okay, so what we're looking for is where the top of our object actually is when we're done. Well, the top of our object is down here, right? The bottom of our object will still be on the principal axis. So what have we got? We've got an upside down image, upside down, smaller, and it's a real image because it's on the same side of the mirror as the object. Okay, there's one more rule that we can use to find the intersection of the lines, right? So we've looked at the red one, we've looked at the green one. Another ray of light that we can draw is the blue ray of light, right? The blue one starts at the top of the object. Now it goes through the center point, right? Top of the object through the center point to the mirror, and at this point here, it's coming in as a perpendicular ray of light. So what's going to happen? The angle of reflection is 0. The angle of incidence is 0. So it's just going to reflect back on itself, right? So it comes in, it goes back on itself. So where's the image? Well, it's in the same place it was when we had the 2 rays of light reflecting, the green and the red. It's the same place, okay? We only need 2 of these rules to actually find the point where the image is. But sometimes it will be impossible to use one of the rules, so we have to use the other 2 rules, right? Usually, for most instances, we can use all 3, but there will be occurrences where we can only really use 2 of them, okay? All right, so ray diagrams are nice, but they're really only going to give us an approximation of where the image is, all right, and what it's going to look like. And because this is physics, naturally there's an equation that goes along with it. And fortunately for us, it's a reasonably simple equation. And here is the equation. 1 divided by the focal length, all right, that's the f, is equal to 1 divided by the object distance plus 1 divided by the image distance. Okay, so reasonably simple equation. So let's say that we have a mirror out here. That's not a very well drawn mirror, but that's okay. And we have a focal point here, and we have an object out here. And let's say our focal length is 20 centimeters, and our object distance is, let's see, that looks like if that's 20, that's about 45 maybe, 45 centimeters. And I would like to know what my image distance, or where my image is going to be, all right? So if I use my equation here, I get 1 over f, so 1 over 20 is going to equal 1 divided by 45 plus 1 over di. Now the easiest way to do this, to solve this, is not trying to find, common denominators and all that stuff. Just plug the numbers into your calculator. So 1 divided by 20 is 0.05, right? And that equals 1 divided by 45, which is 0.022 repeating, all right? And now I would like to know what di is. So it would be 0.05, all right, minus 0.022 repeating because I took this and moved it to the other side, is equal to 1 over di. Now don't remember not to forget the 1 overs, right? We already took 1 over 20 and 1 over 45, but we still have 1 over di on the other side. So 0.05 minus 0.0, I'll put a bunch of 2's in there, is that. We take the reciprocal, and it looks like it's about 36. So the image distance, di, is about 36 centimeters. All right. So if this is 45 out here, all right, the image distance would be, let's see if that's 20, that's 40, somewhere in that range, right about there. Okay. All right, but so this tells us where the image is, but it does not tell us whether the image is upside down or right side up. So for that, what we can do is we can go to the magnification equation, which we're going to do next. So this is the magnification equation, and so this is what we're going to use, right, to figure out what our magnification is and whether it is upside down or right side up. And here's the rules that you can use to figure that out. So if we end up with a positive magnification, the image is upright. If we end up with a negative magnification, the image is inverted or upside down. Okay? If the magnification is greater than 1, right, it's enlarged. If the magnification is less than 1, it's smaller or reduced. If it's equal to 1, it's the same size. So let's see what we get. So m is equal to negative di. Well, di, the image we happened to get was 36 centimeters, divided by the original object distance, and I believe that was 45 centimeters. Whoops, 45 centimeters. And so when we do this math, 36 divided by 45 is 0.8. So m, in this case, is equal to negative 0.8. So what does that tell us? The negative tells us that the image is upside down, so it's inverted. The negative the fact that it's 0.8 or it's less than 1 tells us that this is going to be a smaller image. So it's smaller and it is inverted. Okay, so these are the equations that we'll be using. Magnification equation, and then the mirror lens equation, which is just 1 over f equals 1 over do plus 1 over di. Okay, so those are the equations we're going to use for geometric optics. Okay, and again, we have another example here. Let's say that we have a concave spherical mirror. Okay, we have that has a focal length of 10 centimeters, so f equals 10 centimeters. All right, we would like to locate the image for an object that has a distance of 5 centimeters, so do equals 5 centimeters, right? And we want to describe the characteristics of the image. Now, if the object is very close to the mirror, it is between the mirror and the focal length. So think to yourself what kind of an image you get when you hold that concave mirror, that bathroom mirror, very close to your face. Well, I'm going to predict that we're going to have an upright image, right? And it's going to be larger. Okay? Because otherwise, if I had an upside down image in my bathroom mirror, that's not going to do me a whole lot of good with like putting makeup on and stuff like that. So this is my prediction. Right? Let's see what happens when we plug in the values. Well, we plug in the values. We have our focal length. We have our object distance. We want to solve for di. Di turns out to be negative 10 centimeters. Right? So di is negative. That tells us that if the image distance is negative, that it is a virtual image. Okay? The image, and for a mirror, that means the image is on the opposite side of the mirror as the object. Okay? So it's a virtual image. Now let's see what we can get from the magnification. All right? So m is negative di over 5. So m is going to be negative 10 divided by 5 is 2. All right, so it's a positive 2. Positive 2 means it's going to be a larger image, right? Because that's the magnification of it. It's positive, which means it's going to be upright. and that's exactly what we predicted, and that's what we got. Okay, so I hope that helps. There are other videos out there. There's another video out there that has to do with ray tracing and ray diagrams for lenses. It's very similar to this. The rules change a little bit as far as virtual images, mainly as far as virtual images and focal points are concerned. But the concept is all the same. So I hope that helps, and have a great day.